All right, let's resume our class. Today we are going to move to a new topic called dynamic programming. This topic is not going to be included in midterm. So for midterm, like let's just talk a bit about midterm before we proceed to talk about this section. So for midterm, we are going to do the midterm starting from this weekend. As I mentioned, we are going to do a take-home midterm. So probably like in either Thursday or Friday, I'm going to send out the midterm, and I'm going to let you to give you somewhere between 5 to 7 dates, depending on the how many problems I'm going to give you, to so that you are given 7 to 5 days to complete the midterm, and after that you just send back your solution to us. So basically, you should just treat that as another homework assignment, except that you are not allowed to discuss with each other. So we will take it very seriously if any two of you have the problems that are very too closely resembles each other, right? So in the homework assignment, I usually will just let this go, and actually we do encourage you to collaborate with each other. But for the midterms, please work on the problems on your own. And we are going to send out more announcement about the midterm, independent, like in parallel to the lecture videos. So today we are going to move to a new topic called dynamic programming, right? So in the last sector topic, it was divide and conquer, and before divide and conquer, it was greedy. Before greedy, it was graph algorithm. So as you can see that after we cover the graph algorithm, we gradually move to more and more complicated algorithmic techniques, right? Starting with a very simple and naive set of algorithms in which when you just keep making like locally optimal decisions, eventually you will get something globally optimal. And then we move to more complicated things to about the divide and conquer. It's really about how can you carefully divide the problems into smaller ones and to solve each of the smaller problem. And then usually you need to try to be a bit smart when you try to merge the solutions of two subproblems and in order to come up with the final solution for the larger problem, right? So the dynamic programming is another more sophisticated algorithmic design principle, right? So basically it resembles the flavor that when you want to solve a problem, you want to reduce the problem to a smaller one, but then you cannot exactly do divide and conquer, right? You really have to divide your problem into smaller and overlapping ones. And in order to speed up, you need to do a bit of a memorizations, right? So I'm going to unfold the techniques that's developed under this dynamic programming umbrella, like gradually in the next few lectures. So let's move to the actual content, right? As I mentioned just now, right? So we were sort of like walking through the topics that's discussed in this slide, right? So we started with our discussion of the greedy algorithm. This is a relatively simple algorithmic principle, right? You just keep making the local optimum decision, right? And then we sort of move to divide and conquer and make things a bit more complicated, and eventually we are sort of at the dynamic programming, and then the real definition is that we really need to break up a problem into a series of overlapping subproblems and combine the solutions to smaller subproblems to form a solution to the larger subproblems, right? So there's a little story about the dynamic programming here, right? So basically, it's really just a good to know fact, right? So this is a very fancy name for basically, as you can see later, it's really just for caching intermediate results in the table for later use, right? So there's a story there, right? So basically, the inventor of this set of technique, his name is Richard Bellman, and then we are actually going to talk about one algorithm that's named after that, like that's called the Bellman fault, like that's an algorithm for solving the shortest path with negative edges, right? This person was used to, I think, work in either the federal agencies or AT&T, right? One of them, maybe both. And And when he sort of want to promote his own research, at that time, the Secretary of the Defense had the pathological fear of doing mathematical research. So Bellman just figured that maybe if he can come up with some names of this for this technique that's not very comprehensible for the Secretary of the Defense or whatever funding agencies, maybe they will just let him go and do his own research. Otherwise, it's actually quite irritating to talk to the funding agency all the times to make sure that we are not getting into the research directions they don't like, right? So basically, in other words, it's really this kind of dynamic programming. It's not incomprehensible. It's not comprehensible when you sort of read from the topic from this name. Unlike like greedy algorithm, divide and conquer, right? So you really can sort of more or less immediately see what those algorithms are about. But for this one, I think the inventor is just right intentionally making this critic and not comprehensible. So now this slide basically says that dynamic programming is really a very fundamental technique that has been applied everywhere, right? Inside and outside computer science, right? In computer science, when you do the compiler, you do the system design, and even you do a lot of theoretical computer science, this kind of DP technique just appears everywhere. In fact, outside computer science, operations research and information theory also heavily relies on this kind of dynamic programming things, especially in operations research, when their focus is really mostly about how do you allocate resources, right, over the time and over the space, right? So this kind of allocation problem usually can be reduced down to some sort of like planning problems that can be solved by dynamic programming, right? So in case you do a bit of courses in the math department, and that gives you a bit of exposition of the operations research, and then basically you will see what I mean, right? And this is a list of famous algorithms. Personally, uh, right. So basically, the diff, I think a lot of you have been using that, right? It's really about trying to understand what's the key difference between the two documents before you edit and after you edit. That's a very handy tool for editing source codes, right? So this Viterbi algorithm, I think it's widely used in machine learning and artificial intelligence. I think even you haven't heard about that at this moment. If you get into this area, more or less, sooner or later, you are going to hear about the details of this algorithm. Bellman-Ford is an algorithm we are going to talk about in this class, and other things. It's I think it's the I don't know. Like actually, for the rest of them, I actually haven't heard about that. Right? But I'm pretty sure they are pretty important in their own area. Right? So, and in case you look into the books that has been published on the dynamic programming topic, like you will be very surprised. Like turns after turns of books like that are just published on this particular topic, right? So, have I seen any books that I read myself? I think the neurodynamic programming one, I think it has been a classic one. At least at my time, like a lot of students or my classmates have been reading this book. And also, another thing that's pretty interesting is that when if you are doing the tech interviews in places like Google or Facebook, DP is actually one of the most advanced techniques they can interview you, right? So, basically, when this kind of tech companies interview you, like they start with a phone interview, and after the phone interview, they are going to do an on-site. Maybe these days it's not on-site; it's a Zoom interview, right? It's continuous to do some remote interview, but the key idea is that they sort of want to be able to see whether you are able to solve a tiny concrete problem on the fly within a window of 30 minutes or an hour, right? So that basically means that they cannot ask you over sophisticated questions, right? The questions that appear in most recent research papers, right? That basically you cannot just do that like within an hour or so, right? And also like they cannot ask you excessively simple questions, right? So if you look at the some of the interval scheduling problems that appear in the greedy algorithm we talk about, or if you look at the merge sort, quick sort, right? If you just practice long enough, you can implement all this algorithm within 10 minutes, right? Those are actually at the easier end, right? So that basically means that they are not left with too many options, and dynamic programming is actually one of their favorite, right? You can really make up very difficult computer science algorithm questions whose solutions rely on dynamic programming, right? So, and on the other hand, so long as you sort of see through when the problem can be solved by a dynamic programming, and when you translate your pseudocode or your algorithmic idea into concrete source codes, basically usually this can be done by within 30 to 50 minutes, right? That's within the right time frame for the interview questions, and that's the reason that it's dynamic programming has been one of the favorite questions for the big tech interviews, right? So maybe like the entire point here is really just to make sure that you are motivated to study this area or this topic. Sometimes for some of the reasons is that A is important to you, and I think for a lot of students, it's also important to be able to pass through the interviews from the big techs, right? So, as I mentioned, we are going to talk about two problems today. One would be the weighted interval scheduling, right? So we have been talking about interval scheduling in the greedy section. Now we are going to generalize this problem and sort of see that the greedy algorithm doesn't work anymore. And then we are going to talk about the segmented least squares, right? So the high level idea is still really about trying to convey you the most of basic principles when you use DP to design new algorithms. So now, let's move to the weighted interval schedules, right? So, our good friend, a good old friend, comes back. We want to do the scheduling right here again, right? So, here the setting is one of the setting we have seen. We assume that we own one classroom or one computers, and there are a set of jobs or classes that needs to be scheduled, right? Let's just stick to the computer versus the jobs, right? And each job has a starting time and the finishing time, right? So basically, these are really the jobs that not only the length of the job is fixed, that we also require you to start the job at a particular time, right? Just recall that if you were in Google, a lot of jobs need to be started at a particular moment. For instance, in the midnight every day, we have to retrain the machine learning models, whatever statistical models for Google, in order to make sure that it is able to answer the queries people more interested in, like in the most recent time. For instance, maybe after our president get the coronavirus, like a lot of people just want to search like what's going on, right? A lot of new questions comes in, and the Google sort of need to capture this new dynamic and spikes of the change of interest among all the users. And in order to capture that, right, Google has to do the retraining of its new natural language processing models, or do the retraining of its the search engine models in order to serve for next day's query, right? So that's the reason that Google not only need to train the new models every day, it also needs to train the new models that start at a particular moment, and that was the motivation, right? We sort of talk about the motivation when we were talking about the interval scheduling. So let's just reiterate that each of the job has both a starting time and ending time, right? So the ST and SI and FI, right? So, and the only difference, right? The only difference between this interval scheduling problem and the interval scheduling problem we talked earlier is that whenever you finish a job, there's a cash award or reward, right? So for instance, maybe the first job it versus $100, and the second job versus $200, and so on and so forth, right? So you can sort of see that the value of the job may not necessarily be proportional to the length of the job. Sometimes a job is very critical, but it can be executed within very small amount of time, right? So there's not necessarily any relationship between the reward you are going to get and the resources you are going to commit in order to tackle the problem, right? So the question is still pretty simple. Imagine that you own the classroom, you own the server. Are you able to pick up a subset of jobs you can execute, and so that you maximize your total award? Right, again, like there's a little thing that we just want to re-emphasize, that we are not allowed to schedule two jobs that are not compatible with each other, right? So recall that what is the compatible, right? So basically, if you have two jobs that doesn't overlap, then it's compatible, right? And then if we have two jobs that overlaps a little bit, and that's called a not compatible, right? So we are only interested in subset of jobs that can be executed by the same server, which means that whenever you output a subset of these jobs, if I pick up two arbitrary jobs into this subset, they cannot overlap. They have to be compatible, right? That's the definition of the compatibility, right? So we do want to be able to solve this problem. And also, let's just recall that what did we do when the cash when the value of each of the job is uniform. Basically, that means that the award you get, regardless of the index, regardless the type of the jobs, and then the execution type of the job, it used to be uniform in our previous lectures, right? So in the sense that, like, if I have this instance, regardless which job I solve, I decide to run, I'm going to get one uniform $1 award, right? In that case, right? So just in case, right? In case the award is uniform, that's we sort of can recall that what's the optimum solution over there, right? The optimum solution basically is the earliest finishing time, right? So basically, for this particular instance, if I sort everything by earliest finishing time, then basically A less than B less than H, right? So what you need to do is pick up the A's job and pick up the H's job, right? So in this case, indeed, if you decide to not to execute B's job, you execute two jobs, right? So that's the optimum number of jobs you can execute, right? That's the maximum number of jobs you can execute, right? But under our new rule, it's not necessarily true that the more jobs you execute, the more reward you are going to get. For instance, imagine like this particular setting. If this problem tells you the job owner tells you, right, B is very long, but its value is very high, right? Let's just assume that its value is 999. And A and H are very short, but its value is also very small, right? When you say the value or the weight, right, mentioned here, right, you can just imagine that this is the cash reward, this kind of cash reward, right? Right. That basically just means that if I manage to execute B without executing any other things, my cash reward will be $999, right? So, but if I only execute A or only execute H, I'm going to get $1 each, right? So even that I managed to execute both A and H, I'm only going to get $2, right? So basically that's an example, right? So in case I'm executing A and H, I'm going to execute this is the number of jobs I'm going to execute is maximized, right? Maximized, right? But that's not necessarily true, the maximized profit. Right. When you want to maximize the profit, this is actually the optimum solution, right? The optimum solution only executes B, right? So that's sort of you can see that the generalization of this the interval scheduling problem sort of changed the landscape and algorithmic structure of the underlying problem, right? So it seems that we're solving a different animal. The originally optimal solution may no longer be an optimum in this particular setting, right? So how are we going to tackle this problem, right? So basically we are going to first come up with a recursive solution, and we are going to let you know like how this recursive solution can be implemented efficiently, right? So our recursive solution basically we start with one convention. Basically we want the jobs to be ordered in ascending orders of the finishing time, right? So this is an example, right? I have that many jobs, right? And the only thing I'm talking about is that I'm going to index all the jobs 1, 2, 3, 4, 5, 6, 7, 8, right? So the index of the job is it's indexed by the finishing time, right? Finishing time of the first job is less than finishing time of the second job, less than finishing time of job of the third job, and so on and so forth, right? So if you look at the starting point, it's not necessarily true, right? The starting time of the third job is still smaller than the starting time of the first job, right? So basically if we look at the starting job time of the jobs and walk through the indices, and then there's no pattern at all, right? The starting point will be the third one, and then first one, second one, and then fifth one, and so on and so forth, right? This has no pattern. We just need to focus on that sorting all the jobs according to the finishing time, right? So we should also define a function called pj, right? Pj basically in English is really just the largest index I that's smaller than j, such that job I is compatible with job j, right? So let me just give you an example, right? So let's say this is 6, right? I want to compute the p6, right? So the sixth job is the time span of the sixth job is between 5 o'clock to 9 o'clock, right? So I'm going to find something, right? So I need to find something from 1 to 5, right? The index I smaller than j, such that the job I is compatible with j, right? So I need, if I say I need to say I need to find the largest I, so that the index the job I is compatible with job j, right? So let me just give you an example, right? So if my I were 5, right? Let me check I equal to 5, right? It's obvious that the index here, the fifth job, is not compatible with the sixth job, right? So I cannot be 5, right? So if I look at 4, again, I come to the same conclusion. Look at 3, I come to the same conclusion. But as soon as I start to look into 2, right? So I sort of realize that, well, the ending point of 2 is the same as the starting point of 6, right? So 2 is compatible with the 6, right? So not only that, I saw it's 2 is also the largest, right? Anything that's larger than 2, we can just 3, 4, 5. It all doesn't work, right? So basically, that means that the if I look at here, right here, right, the p of 6 equal to 2, right? That's the reason here. Right, so I can also check p of 7, right? P of 7, again, like, let me just erase everything and see whether the definition makes sense to us, right? So p of 7 here, like, let me look at the 7 here, right? 6 is not compatible with me, 5 is not compatible with me, 4 is not compatible with me, but if I look at 3 start to be compatible. Not only that, right, this is f3, right? f2, because f2 is going to be smaller than f3, so 2 and 7 are also going to be compatible, right? So a consequence of this definition means that for any I prime that's less than or equal to I, right, I prime is compatible with j, right? So anything that's smaller than 3 that are compatible with the 7th job, right? So that's the reason p7 equal to 3. Right. We also have p8 equal to 1, right? So because if I do that again, only the first job is compatible with the 8th job, right? p8 equal to 1, right? So if you look at all these two things, right? So another funny thing that's sort of a quite interesting property we have is that p is not monotonic, right? Monotonic, right? It's p8 is actually smaller than p7. That's that's actually we have been talking about this for minutes. It's really just to highlight that there's a convention we are going to use. It's ordered by the finishing time, right? And we do define a function called pj and walk through all this example to give you some intuition of how pj should be computed. So now let's use the whiteboard to start sort of get into the most important message here. So we do want to be able to use recursive functional forms to solve this problem, right? So let's just assume that we have an input that looks like that, right? This is first job, second job, third job, and fourth job. Actually fourth job, right? And let's just assume we are doing something like that, right? So we have 4 jobs: job 1, job 2, job 3, and job 4, right? So now let's so basically I'm sort of outlining the sort of the what's called the syntax, right? Syntax of dynamic programming. What does that mean? That means that like it's you. Although like in every single individual algorithm, algorithm problem, you sort of need to sort out your own intuition, in order to design the right type of DP problem, right? But there are some syntax you should follow. You should be able to follow, right? The first step is to define as what we call the optimum function. Optimum solution of function, right? So let me just walk through, give you a concrete example, and then you sort of by just looking at this example, so again and again, you sort of develops the intuition what we are talking about here, right? So we define the optimum OPT I or J, let's call that J, to be the max weight of any subset of mutually compatible job for subproblems. Problems that's from of jobs 1 up to J, right? So it's the whole language is a bit convoluted. That it's really just that if I have OPT 1, that basically means that I sort of want to solve this problem with only instance 1 here, right? So 1 means that there's only one job, and the job is really just the first job here, right? So basically the question here is really just asking that what is the what's the optimum solution for the problem that consists of only only job 1, right? So this optimal solution is quite obvious, right? So in order to I don't even need to look into the award you are paying me. If there's only one job, I just pick this up and pick up whatever cash I have, right? So, and let's also look into what is optimum 2. Optimum 2 basically means that I ask you to solve the problem, but let's you just consider this the first 2 subset, right? You should pretend that this 2 things doesn't exist, right? So basically if I walk to here, that's sort of the problem you want to solve, right? This is 1, this is 2, sort of this is matching here, this is matching here, right? So what's the optimum solution for jobs 1 and 2, right? When I say optimum solution, basically I mean that I want to find a subset of mutually compatible jobs that maximize my return, right? So if I have OPT2, right, for this particular example, right, these 2 jobs are not compatible with each other, right? So I had to exclude one job, and like after I exclude that job, there's no reason for me to not include the remaining jobs, right? So the optimal strategy basically just compare the return, right? The return from doing job 1 against the return, right? Return from doing job 2, right? So for instance, if the return here is $100 and the return here is $75, like it's basically a no-brainer. I'm going to pick up the one that's more expensive to me, right? So that's the definition of OPT2, right? So we can continue and then say what is OPT4? OPT4 basically means that can you find a solution for the first job, four jobs, right? So if we have the jobs that looks like that, right? Let me just copy and paste, right? That looks like that, right? What's your optimum solution, right? So optimum, this is the optimum solution for the job 1 to 4, right? Right. So basically, this is the definition of OPT, right? In general, I want to solve the OPT n, right? If all the jobs are considered. What's the how can we choose a subset? Find the subset that maximize return. Right. That's the problem. That's the issue. That's the problem we are trying to solve here. Right.